Hello everybody and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 2 and the topic of the lecture is introduction of MOS and energy band diagram. Let me give you an agenda of the talk. We have already finished, we will introduce to you the subject initially and then we are going to the class number 2 here today and explain to you. So, the outline of this lecture will be basically give you an idea about the MOS structure itself, metal oxide semiconductor. Look at MOS silicon substrate properties, right. When I say properties, I mean to say material properties in terms of its structural stability and its electrical properties in terms of charges which are there in the silicon substrate. We will look at the basics of Fermi energy concept and then look into the band diagram concepts, and this is where it is very important to understand what information does the band diagram give to a device physicist. Finally, when we have understood MOS and we have understood what is the structure of the MOS and the electrical characteristics of a MOS, we will take it up the MOS capacitor with biasing, which means that now I will bias the MOS capacitor by an DC bias, preferably a DC bias now. We are not giving any AC signal to this time around, we are giving a DC bias and see how does the MOS capacitor actually behave. So, when I say biasing, we refer to this as a DC biasing, right. We refer to this as DC biasing and there is no AC biasing as of now. This is your energy band diagram which we will be studying here. Now, finally, the last part of the lecture series will consist of depletion layer thickness and we will see how it is related to the bias and the doping concentration. We will look into surface charge density and then have a look at the work function differences, right. What is the meaning of work function and how it is, what does work function difference imply from the device point of view. So, this will be the basic outline for this course structure. Very first thing first, let me give you the top level view of the MOSFET and then we will go to the 2D structure. So, what you see on the top right corner, which is this one, is the 2D cross section of the MOS structure, and what you see on the left bottom left corner is basically the 3D structure of a MOSFET. MOSFET is metal oxide semiconductor, FET is field effect transistor. Let me tell you why this name has come. Field effect transistor comes from the fact that the electric field is responsible for the charge carrier movement in any of the structure. We refer to that as a field effect transistor. And why is it known as a transistor? Because you are transferring sort of resistance from input to output. Your input is typically a high, in this case having a high resistance and the output is relatively a low resistance. So, therefore, it is known as a FET device. Why it is known as a MOS device? Because it is, if you look at the structure which I will just show it to you, is basically a metal oxide semiconductor. So, if you look at the right structure here, it consists of a p type substrate. So, what you do is that you grow a p type substrate, which is this one, right, over which you grow n plus layer. N plus is heavily doped n type layer, but these are all, this is basically heavily doped, right. This is heavily doped. Heavily doped basically means that it is much larger than the intrinsic carrier, right, and the number of charge carriers are relatively very large, which means the number of holes at this particular point in the substrate is very large and the number of free electrons in this drain region and in the source region is also very large. So, if you look MOSFET from an external viewpoint at 2D cross section, let us not talk about 3D here, let us talk at 2D. It is basically a 4 terminal device with the one terminal known as source, right, the other is known as the drain, right, other is known as the drain and the third one is known as the gate and the fourth one is known as the body here, also referred to as a body of the transistor, or it is also referred to the substrate, right. So, these are the 4 terminal of the device. Blue colored, light blue colored area is p type substrate having larger number of holes. The brown colored or black colored area is having large number of electrons, right. And now let us concentrate as we move from gate towards the channel region. I will explain to you what. So, this is basically your metal, followed by an oxide layer, right, and then you have a semiconductor. So, what is the structure? If you look very carefully, it is metal oxide semiconductor, and hence the name MOS. Is it clear? So, the reason it is known as a MOS is you have metal followed by an oxide layer followed by semiconductor. The obvious reason asked is why MOSFET, why silicon MOSFET, right. You should know all these, the basic concepts which should be clear to you before you move forward, that oxidation of silicon is very easy and relatively a very easy task, which means that if you can keep a wafer right here in front of you and wait for about an hour or so, you will see a thin layer of white crust over the silicon wafer, right. And the reason is that silicon wafer will actually start to oxidize as you keep it in the air, right. So, the formation of MO layer, metal oxide layer, right, is a very normal and energy wise a very stable process. So, the growth is very easy. Beyond oxide you grow a metal layer. So, you see I have grown a metal layer here in front of the oxide, right. The thickness of the oxide layer is referred to as T suffix OX, right. The distance between these two lengths, between this edge and this edge, is referred to as a channel region or channel length. This is known as channel region. The channel length is basically referred to the length of the gate. So, how much length of the gate is there, this is channel. In this case, if you see, your gate is basically overlapping over the drain on this side and overlapping over the source on this side, right. And this is the part where you will have the inversion layer. We will come to the MOS structure later on, but this is the structure which you see here. In all the respects, in all the cases, source is generally grounded. So, you have source is generally grounded, you ground the source always in most of the cases. Drain you apply a bias, right. Gate you apply the input signal, right. You put the input signal or a DC signal and you get the output from the drain. Body at this stage, early stage, let me say this is also grounded. So, body and source are grounded, but gate I am applying an external source and drain I am applying an external source. Both are as of now a DC bias. With this knowledge you have gained, let us come to the left hand corner part here. If you see very carefully, the third dimension which is in this direction is basically my width. This is the width, right. I have already written it down, this is the width. So, the width of the MOSFET is in the third dimension, which is inside your computer screen, right, and length is along the computer screen, right? And if you look very carefully, the source, drain and gate drain are shown in this region, right. And then these two, this is one MOSFET, there will be another MOSFET which will be nearby. We can actually separate them by using oxide layer, a thick oxide layer, so that there is no shorting between the two gates. But I need to, at this stage I need to look into this part. This type of device which you see in front of you at this stage is basically, this device is known as N MOSFET, right, N channel MOSFET, and it is also referred to as enhancement mode MOSFET. I will enhancement mode MOSFET. I will recommend you that once you go back to once you finish this slide, or you can stop the video now and go to your book and have a look at what is the meaning of enhancement mode MOSFET. We will look at it at a later date, right. This gives you a basic understanding of my 2D structure. So, I have given you in the first slide, I have given you a holistic structure of MOSFET. Now, we will be breaking it down into smaller structure, and the first one is basically we use MOS as a 2 terminal device, right. We will use MOS as a 2 terminal device and we will use it as a capacitor. As you can see on the right hand side, the previous slide, if you look, let me help you, let me explain to you what the previous slide. In the previous slide, I am expanding this block here. This block I am expanding here. The red colored square block which is shown here is being expanded in the next slide, right. On the right hand side, you see, this is the gate metal which you see, right. Then you have the oxide layer and then you have silicon. So, this is MOS, this is M, this is O, this is S. So, your semiconductor can be a N type semiconductor, it can be also a P type semiconductor, correct. And now you have this gate, you have an oxide material and you have a semiconductor material available. We are at this stage not going into the fabrication process steps, but I will assume this to be as a 2 terminal. Where are the 2 terminals? The first terminal is the gate terminal, right. This is terminal number 1, we will assume it to be terminal number 1, and this is substrate is your terminal number 2. So, there are 2 terminals, terminal 1 is on the gate metal and terminal 2 is the oxide material. Now, the gate material can be actually polysilicon or metal, right. In most of the cases it is metal, but many people used to have polysilicon also coming into picture, because polysilicon's behavior is almost like a metal, right, and its resistivity is very, very small. If you come to the material of the oxide can have the most commonly used is silicon dioxide, a common sense, no need to worry about. But after silicon dioxide you can also use hafnium oxide, aluminum oxide and all other forms of oxide as well, right. So, the insulated material, you have variety of insulated materials which can be fit between the gate metal and the silicon, and the substrate as it is written here on the diagram, on the schematic here, it can be either N type or P type, right. And of course, the conduction will depend on the majority carriers in the substrate. So, if the majority carrier is N type, and then more number of electrons which will be deposited, and if you have P type you will have more number of holes. I will just, before I move forward, I will just give you one small hint, and then you must have studied it already, but I am just give you a small hint and show it to you. So, let us suppose this is metal, right, this is metal and this is gate basically, and I have an oxide layer here, right, and I have an, let us suppose, let me make it easier for you, make it an N type semiconductor here. So, N type semiconductor effectively means you have large number of electrons. Now, if you give a positive bias on the metal, if I give a positive bias on the metal, the electric field will be all directed, and if I give the second terminal is grounded, let us suppose, the electric field will be all directed inwards into the semiconductor. This will be the direction of the electric field. Since the direction of the electric field is downwards, the electrons from the substrate will be pulled towards the this interface. This interface is referred to as silicon dioxide interface, right. So, as you give a bias, a large number of charge carriers get accumulated near the silicon dioxide interface, right. When you give a negative bias, all the electrons will be pushed backwards, and whatsoever small holes are there will be attracted. But please understand, when you have an N type semiconductor, your electrons will be the majority carriers, but you will also have a very minuscule number of holes available there. They are known as minority current carriers, right. So, I will just name a few of them and I will explain to you what I am talking about, and let us take up a basic MOS device which is already there in the initial discussion. Then if you take a MOS device, then it looks something like this, right, two terminal device. I have a metal here, so this is metal, right, this is metal. I have an oxide layer here, right, this is the oxide layer, and of course, this is semiconductor. This is my gate terminal, this is my substrate. Let me short gate and substrate, right. It primarily means that substrate is also referred to as a body. So, Vg is equals to Vb, which means my gate potential and my body potentials are exactly the same, correct. Once you have done that, what we will do is that let us move from this terminal as you go inside this through the substrate or body, and then we come back again back to the gate material. Then we can write down that sum of all the contact potential, right, contact potential from gate through external connections to bulk or body will be given as phi of gate material minus phi of bulk material. Phi is a potential, is known as a contact potential. So, the difference will be primarily the contact potential of the gate minus the contact potential of the bulk, correct. So, that will be how you define the value of your the sum of the potential, which means that if you want to cross your charge carriers from gate to the bulk through these layers, you have to give an external potential of phi gate minus phi bulk, right, negative of that in order to cross this potential barrier, correct. And we define this to be as the sum of all the contact potentials which are available, right. With this knowledge or with this idea, let me show to you the various factors which affect the gate potential in this case, right. So, first factor which comes into the mind is basically the charge carriers, which means that, let me draw for you a diagram here. So, that is easier for you to understand that I have this gate material here, and then I have the substrate material at the back side. This is my body, and then I have the substrate material here. Let me shade it off. This is the substrate material on the back side, and I have this metal interface and a gate interface. This is my oxide. Of course, the prevalence of free charge carriers in oxide is very small. So, if I assume that this side has got negative charge carriers, right, this surface will have a positive charge carriers. This is a mirroring action which will happen. You will ask me why we will have negative, because let us suppose it is a metal having a large number of free electrons available. I would expect to see equal number of positive charges being mirror charges being accumulated on the semiconductor side, because charge neutrality can never be violated in that sense, right. So, that is the reason I show you this negative and positive values, and what I do is I still do this, I just short gate and bulk in the sense and try to do it in this manner. Once you have done that, let me ask you a question and see how you can answer, or you can think about it. Can we apply an external bias between gate and bulk so that I will be able to make this net charge disappear? My net charge is still 0. By applying an external bias, can I effectively remove these charges, these negative charges and positive charges, right. So, the next question which you can ask is that can an external voltage right be applied for making this potential or this charge go to 0. This is the question which I am putting forth in front of you, right, that can you apply an external bias. Now, if you want to make the total potential, let me make the total potential 0, that is the whole idea, right. So, let me make the total potential 0 in this case and do one thing, that I write that if I write down that phi of ms will be phi of bulk minus phi of gate. If you add this to this, right, you see the net is 0, because it is minus bulk here. So, this minus bulk will get added with plus bulk, and plus phi gate will added with minus phi gate, and final voltage which will be developed, the charge will be developed will be 0. You get the point, right. So, you have to apply a bias equal to phi bulk minus phi gate, which is just the negative of the previous case. Once you do that, you ensure that your charges are going to 0, right, the total charge is going to 0. Now, this is the total external potential. Now, let's break it down, that the phi gate and phi bulk, what are the various components of charges in this phi gate and phi bulk, because then if we know what are the components, I can actually reduce its value by whatever methodology is available to us, so that I have to apply a lesser amount of a negative voltage in order to switch it off, right. That is the overall concept which I wanted to showcase in front of you. Now, this charges consists of 4 parts, right, and we will go one by one for these 4 parts. The charges consists of 4 parts. What is the first part? I will come to that first part now and show it to you. The first part, of course, is your oxide fixed charge. Oxide fixed charge, and they exist very close to semiconductor interface. So, let me show where the semiconductor interface is, right. I can show it to you here, maybe I will not draw it once again. You see, this is my silicon interface material, this is my this is my silicon dioxide interface, right. So, these charges are very close. Let me write that down. So, this the first charge is the oxide fixed, as the name suggests, it is a fixed charge, right. It is not a movable charge. So, even if you apply a bias, they will not move across the oxide layer, and they are fixed in nature, they are ionized particles, and they are found near the oxide semiconductor interface. So, the region of formation is silicon dioxide interface. That is one thing which you should be aware of. And the second part which you should be aware of is that they are formed while you are actually fabricating the oxide. There are many techniques by which you fabricate oxide. So, when you fabricate oxide, there are chances that impurities goes inside the oxide layer, because the distilled water used is not of proper, there are certain ionized impurities there, and where they will sit in the oxide layer, and there will be positive and negative charges available to us, and there will be some charges, fixed charges within the oxide layer, right. Now, this and interestingly, this fixed oxide charge is independent of all biases, right. They are independent of all biases, doping, right, doping, which means doping concentration, and oxide thickness. It is independent of that, independent of all biases, all doping concentration, and all oxide thickness. They are independent of that, and they depend primarily on the fabrication procedure steps. The second one is referred to as an oxide trap charges. Please understand, this has nothing to do with the applied bias. This has come because of certain reasons while you are forming the MOS layer, right. So, the oxide charges can exist throughout the oxide, but it is usually close to either of the interface. Either the interface means it is either close to, so it is its location is very close to either silicon dioxide or silicon dioxide and metal interface. These are very near to this, either metal gate or the substrate, and they are formed primarily because of 2 or 3 important points. One is due to radiation, which might be optical or nuclear. This can be also due to photo emission, right. This will be due to photo emission or injection of some high charge carriers. So, if you do high energy carriers, so if you do a large, so if you do let us say you are doing Gaussian doping, right, and you are using ion implantation machine to do it. So, these are very energetic particles, right, and they will just bang through the metal layer and sit in the oxide layer, and these are known as oxide trapped charges. So, they have been trapped by an external source. Let me come to the third one, and the third one is referred to as a mobile ions or mobile charge, mobile ions or mobile charge. And this is primarily because of sort of exist in the oxide again, and because of sodium ion, because of alkali ions, sodium ion, alkali ion here, because of alkali ions, and this primarily sodium. So, sodium plus happens, and this is primarily introduced by an external environment during fabrication, right, available in many of the cases. However, this charge can actually move within the oxide layer. So, these are mobile, right. You give a bias on the gate side. So, these layers, since this is positive in nature, they will, if you give a positive voltage on the gate sides, they will be pushed near the silicon dioxide interface. So, these are basically mobile charge carriers which are available. These are mobile charge carriers in a sense. Let me come to the last one, which is the fourth one, and this is known as interface traps, interface trap charges. Now, also known as fast surface charges or fast, this is also referred to as a fast surface charge. Now, what happens, the reason the interface are formed is, if you look at the growth of silicon dioxide from silicon, so silicon will give double bond. So, silicon, if you remember, has got silicon will be catenated, right, just like carbon. Now, how silicon dioxide is formed is that it removes this 2 particle from here, let us suppose, then silicon double bond O and then silicon double bond O will come into picture. So, each of the 4 bonds will go, 4 bonds are remaining, these 4 bonds and go to oxygen layer. Now, what might have happened is during fabrication, not all the bonds were saturated, or not all the bonds were able to form with oxygen. So, it might happen that you have silicon double bond O, but the other 2 bond did not get enough time or some problem that they were not able to bond with oxygen. So, these are dangling bonds and they happen to be the interface trap charges which are available there. So, they act as traps. So, if you have a charge carrier flowing through the device, they will trap the charges there and they will be changing the overall structure of the above this thing. Now, what has happened over the years, this is a traditional way of looking at the MOS structure. What has happened over the years, because of our maturity in fabrication and the maturity in terms of fabrication procedure, which is VLSI technology, many of these charge carriers have been reduced drastically to a lower value, right. It is very easy to reduce them to a very low value, and that is the advantage which people face when you have a mature technology in terms of fabrication, that many of these charges are reduced, which means that, go back to my previous discussion, if these charges are reduced, this phi ms which you see will also get reduced, and this affects certain characteristics of the device at later stages, right, and that is what we are going to learn in subsequent classes. Now, let us look at immobile charge carriers in much more detailed manner, and then we will look into mobile charge carriers also in the detailed manner, right. So, let us look at the immobile charge carriers. Now, we know that let me write down a value of the charge Q0 to be the total charge available within the device. This takes care of interface trap charges or oxide trap charges, and let us suppose it is Q0. Q0 will effectively be given as the charge per unit area, which you will find out, and therefore, this is referred to as an effective interface charge. We refer to this as effective interface charge, and this is typically of the order of 10 to the power 10 to 10 to the power 11 ions per centimeter square. This will correspond to approximately 1.6 into 10 to the power minus 9 to 1.6 into 10 to the power minus 8 coulomb per centimeter square. How did I do it? I just multiplied this with Q and I got this value. So, you see, just by having 10 to the power 10 or 10 to the power 11 ions per centimeter square in that small domain, which is effectively interface trap charges, you are able to generate typically the ion charge to be 1.6, charge density to be 1.6 into 10 to the power minus 9 to 1.6 into 10 to the power minus 8 coulomb per centimeter square. So, understand, it is coulomb per centimeter square, it is basically charge density which we are talking about, right. Now, the effective interface traps will be located near the interface of silicon dioxide, right. Now, if you want to discharge this, then you have to apply an external bias whose value will be negative of what storage is here, so that these trap charges get nullified and the effective value is approximately equals to 0. Now, the charge Q0, right, will obviously cause what, minus Q0 to appear in the system. So, if you have Q0 charges, the effective interface trap charges, you require that approximately, so you require a minus Q0 charge will be required by the system to negate the effect of Q0, right. That is the reason you write to be as minus Q0 in this case. So, if I know that Cox is my oxide capacitance, oxide cap per unit area, let us suppose, then I write down a new statement here that psi of ox is equals to minus Q0 prime by Cox prime. So, what is psi ox prime? Psi ox prime is the voltage drop across the oxide layer. So, you understand, Q equals to CV, everybody knows that. So, this psi-ox is the potential across the oxide layer. I am assuming that there are Q0 prime number of interface trap charges per unit area. If I divide that by Cox prime, which is the oxide capacitance per unit area with a negative sign, then I will get the potential across the oxide layer as psi-ox, which is there, where basically my Cox prime can be written as epsilon ox divided by Tox, where Tox is basically the thickness of the oxide layer, and I can write down epsilon ox, the permittivity of the oxide layer, to be equals to K of ox into epsilon naught, that you already know this particular point, where epsilon naught is given by is a permittivity in the free space, and it is given by 854 into 10 to the power minus 14 farad per centimeter, and Kox is the dielectric constant of insulator. And what is the value of Kox? Kox is typically for silicon dioxide, it is approximately equals to 3.9, right. So, we have done the basic idea here, we have finished with this one. What we learned today? We learned today the concept of effective interface trap charges, the meaning of psi-ox, MOS is a 2-terminal device, and we have also learned about the basic concepts of the interface and oxide trap charges, what are the various trap charges available there. We will take next part in the next lecture. Thank you.